In early 1943, American bomber production faced a crisis hidden beneath its staggering output numbers. Factories were working around the clock. Thousands of workers building the B-17 Flying Fortress and the newer B-24 Liberator. Newspapers showed smiling crews standing beside freshly painted bombers, but behind those headlines lay an industrial bottleneck no one had solved. Airframes could be assembled quickly, engines installed efficiently, but one stage of construction repeatedly slowed everything to a crawl: the joining of the bomber's massive fuselage sections. Traditional methods demanded precise riveting by teams working inside and outside the airframe simultaneously. Each rivet required coordination between workers, hammering and bucking bars synchronized by sound alone. A single bomber required over 500,000 rivets. The process was slow, exhausting, and prone to defects. Entire fuselage sections sometimes had to be disassembled and rebuilt because alignment drifted a fraction of an inch. Even at peak speed, completing one B-24 bomber took over 40 days from the first frame assembly to final inspection. The Army Air Forces couldn't afford that pace. Bomber losses over Europe were climbing. Every daylight raid into Germany consumed aircraft faster than factories could replace them. In 1943, U-boat attacks and Luftwaffe defenses were cutting deep into Allied supply lines. The United States had promised to overwhelm Germany with production, yet its factories were already straining. The war in the air wasn't just fought with pilots and bombs. It was fought with schedules, welding torches, and steel jigs. At Ford's Willow Run plant in Michigan, engineers had promised something almost impossible: a bomber built like a car, moving down an assembly line in continuous motion. Henry Ford had bet his industrial empire on the belief that aircraft could be mass-produced the same way automobiles were. The government expected thousands of B-24 Liberators to roll off that line each year. But despite vast buildings, miles of conveyor systems, and tens of thousands of workers, reality didn't match the promise. Planes moved forward slowly. The bottleneck wasn't equipment, it was the method. Riveting required patience, precision, and coordination that machines couldn't yet replace. Then came a suggestion so unorthodox that engineers dismissed it immediately. It didn't come from the design offices or the university-trained metallurgists who oversaw the plant's technical divisions. It came from a welder on the floor, one of the thousands who had joined the workforce when America's men went off to war. Her name rarely appeared in reports, but her idea quietly rewrote the physics of bomber assembly. The woman's name was Mildred Sisk. She worked the mid-shift at Willow Run, responsible for joining structural sections of the B-24's mid-fuselage, the portion that joined the wing box to the bomb bay. She wasn't a designer or engineer. She was a production welder who noticed something nobody else had time to see. Every day she watched riveters struggle to align curved sections of aluminum skin, fighting distortion as temperature and vibration warped the metal. Even the most careful crews left microscopic gaps, forcing inspectors to reject sections that didn't meet tolerance. The waste was enormous. Some partially completed fuselages were scrapped entirely, their frames twisted beyond recovery. Sisk had learned basic welding in a Detroit automotive repair shop before the war. She wasn't supposed to use those skills on aircraft aluminum. Riveting was the standard, and welding aluminum was considered unstable, prone to cracking. But one night in March 1943, she began experimenting on scrap pieces from rejected fuselage skins. Using a torch meant for steel reinforcement, she made small tack welds instead of rivet holes, joining curved plates temporarily before the riveters came through. The idea was simple: stop the metal from flexing and shifting during riveting. Her foreman laughed when she called it her ridiculous little trick. The trick worked. By holding panels rigid with a few quick spot welds, riveters could move faster and hit more precise alignments. The sections no longer needed constant repositioning or clamps. Welds were later ground down and covered by proper rivets, leaving no sign of the temporary fix. What had once required 4 workers could now be done by 2. What had taken days began finishing in hours. Sisk didn't file a report or a patent. She simply kept using the technique during her shifts. Other welders noticed and copied it. Within a week, several teams in her section were using tack welds to hold assemblies together. Supervisors noticed the improvement, but didn't understand why. The production charts suddenly showed mid-fuselage sections being completed in half the usual time. Inspectors reported fewer alignment rejections. The shift foreman, confused, asked his crews how they were doing it. They shrugged. just welding them straight first. When engineers discovered what was happening, the reaction wasn't celebration. Welding aluminum aircraft skins was explicitly forbidden by company regulations. Aluminum alloys used in aircraft were heat-sensitive, easily distorted, and could lose strength if overheated. Welding could weaken the metal at the molecular level, creating microscopic cracks that might expand under flight stress. Riveting, though slower, distributed loads more safely. Supervisors ordered an immediate halt to the unauthorized method. But halting production wasn't easy in a factory running 24 hours a day. As soon as inspectors left, welders went back to using Sisk's trick quietly, because it worked. The gains were undeniable. By April, Willow Run's mid-fuselage completion time had dropped from 12 days to 4. Sections rolled down the line ahead of schedule for the first time since the plant opened. Engineers eventually had to acknowledge that something was happening they couldn't explain, and that ignoring it might cost them the output Washington demanded. An internal review was launched. Metallurgists from the Army Air Force's Materiel Command arrived to investigate. They examined samples from welded sections, looking for cracks or weaknesses. What they found defied expectations. The tack welds, applied quickly and in short bursts, hadn't penetrated deeply enough to damage the structure. Instead, they acted as alignment locks, preventing distortion while spreading stress more evenly across the skin. As long as the welds were removed and replaced with rivets, the overall strength actually increased. The unintentional discovery meant that temporary tack welding could serve as a structural alignment tool without weakening the aircraft. Ford's engineering managers quickly formalized the process, calling it pre-tack alignment welding. It became part of the official procedure within 2 months, renamed for documentation purposes so no one outside the plant would realize it came from a floor welder. Teams were retrained to use controlled tack welds at precise intervals. Production speed skyrocketed. The average time to complete one bomber dropped from over 40 days to less than 10 by mid-1944. The transformation didn't just save time, it reshaped how the factory worked. Before the change, crews had to remeasure, reclamp, and reheat sections dozens of times during assembly. Riveting teams often waited hours for fitters to realign warped frames. With tack welding, those delays vanished. Panels held their form perfectly from start to finish. Fixtures and jigs that once filled entire hangars became unnecessary. The assembly line flowed with a rhythm it had never achieved before. Inspectors began noticing another change. The finished bombers were stronger. Stress tests showed less buckling in the mid-fuselage under simulated flight loads. The pre-tack method aligned frames more precisely than manual clamps ever had. Engineers realized that the ridiculous trick had improved overall airframe integrity. Every time a B-24 rolled off the line without warping, it validated what Sisk had discovered by instinct. By the summer of 1944, Willow Run was operating at full efficiency. The plant covered 3.5 million square feet, one of the largest industrial buildings on Earth. Inside, bombers moved nose to tail down a continuous line nearly a mile long. Engines, wings, and fuselage sections met in synchronized motion. At the end of the line, completed aircraft emerged into sunlight, engines roaring for their first test runs. Crews cheered each launch, unaware that their record-breaking output traced back to a single welder's observation. But as the process scaled up, new challenges appeared. Welders who weren't trained properly began applying full seams instead of short tacks, overheating sections and creating minor cracks. Quality inspectors flagged the issue immediately. The plant needed a way to standardize the technique across thousands of workers. Ford's engineers developed specialized weld limiter torches that automatically controlled heat duration and arc intensity, ensuring consistency. Training programs were established to teach the precise method: center-to-edge tack placement, alternating sides to balance stress, mirroring exactly what Sisk had done by instinct. The irony wasn't lost on a few supervisors who remembered her first reprimand. The process that once violated regulations was now the plant standard. Production soared again. At peak efficiency in late 1944, Willow Run delivered one fully completed bomber every 5 hours, an achievement unmatched anywhere on the world. While the headlines celebrated Ford's industrial genius, no newspaper mentioned the welder whose small experiment had unlocked that efficiency. Her name vanished from reports, her method credited to process optimization studies. But among the workers, everyone knew. They called it Millie's Fix, the quick welds that made the impossible schedule possible. As the Allied bombing campaign intensified, the planes from Willow Run filled the skies over Europe. Every 5 hours, another bomber joined the war, each one built with a process born from a welder's so-called ridiculous trick. By autumn 1944, the system had reached its peak. The rhythm inside Willow Run was unlike anything seen before in aircraft manufacturing. Trains brought in raw aluminum at one end and departed with finished bombers at the other. The line never stopped, not for lunch breaks or holidays. Day and night, the sound of drills, torches, and hammers filled the massive plant. From the air, it looked like a living machine, a single organism built from concrete, steel, and human persistence. Inside, the new tack-welding system kept the flow steady. Fuselage sections moved through stations like clockwork, each crew performing its task with practiced precision. The plant's engineers, once skeptical of the floor workers' innovation, now built entire schedules around it. The numbers told the story. In just a few months, the average bomber completion time had fallen again from 10 days to less than 5. The U.S. Army Air Forces could barely believe the reports. At the start of the war, completing a heavy bomber in that time frame had been considered impossible. Now it was routine. The idea that something as small as a few tack welds could transform production shocked even the most seasoned industrial planners. Ford's managers began sharing the process quietly with other aircraft manufacturers under the label Rapid Prefit Method. Plants building fighters and transport aircraft adapted it for their own lines. The effect rippled across the entire war industry. In bomber plants from California to Kansas, welders began using the same technique to hold complex assemblies steady. In each place, the results were the same: fewer rejected parts, faster alignment, smoother fits. By the end of the year, production across the Allied aircraft network had increased by nearly a third. None of that was officially attributed to Mildred Sisk or her ridiculous trick. Her name didn't appear in records, patents, or newsreels. But on the floor, among welders and riveters, her story spread like a quiet legend. Crews who never met her talked about the woman at Willow Run who had changed everything with a few sparks and a stubborn idea. The technique also changed how the plant thought about skill. Before, welders were seen as secondary, helpers who followed blueprints and orders from engineers. After the tack weld breakthrough, management began to view floor workers differently. Supervisors started listening more carefully to suggestions from the production line. Experimentation was quietly encouraged. Some crews discovered that alternating tack patterns reduced warping even further. Others figured out how to use the same principle to speed up the installation of wing spars and bomb bay doors. The assembly line evolved into a living laboratory, guided as much by instinct as by engineering charts. But there was still tension between the shop floor and the office. Official reports credited the new efficiency to management coordination and process simplification. In truth, most of the improvements came from people who worked with their hands, not clipboards. Engineers in Detroit and Washington took the praise, but the welders knew better. In their break rooms, they joked about the ridiculous trick that everyone now depended on, but no one would admit had come from them. They taped small welding rods to their lockers as quiet reminders of how it had all started. The human scale of Willow Run was staggering. More than 40,000 workers operated inside that single plant, men, women, and teenagers, many of whom had never touched machinery before the war. They came from farms, small towns, and city factories, drawn by the promise of steady work and patriotic purpose. Every shift change looked like a migration. Buses lined the streets, bringing in new waves of workers while others trudged home through the Michigan snow. Inside, each station had its own tempo. Welders moved like musicians, torches flaring in rhythm with the clatter of rivet guns. Supervisors carried clipboards and stopwatches, counting seconds between each completed section. Efficiency wasn't just a goal, it was the language everyone spoke. By November 1944, the Allied air campaign was reaching its height. B-24 Liberators from Willow Run filled the skies over Germany, Italy, and the Pacific. Crews flying those bombers had no idea that their aircraft carried traces of a welder's experiment in every panel. Each fuselage, every wing joint, every riveted seam bore the invisible fingerprints of that discovery. The planes were stronger, straighter, and faster to produce than any before them. Test pilots noticed the difference too. They reported smoother handling and fewer vibration issues during high-altitude flights.
Engineers credited new design tolerances, but on the floor, workers knew the truth. Perfect alignment came from perfect preparation, and that started with the tack welds. As production peaked, Willow Run's methods attracted attention from overseas. British inspectors visited the plant, studying how American industry had achieved such speed. They were astonished at how workers coordinated across such a massive space. Ford's managers explained the layout, the conveyors, the logistics, but not the real secret. The temporary welds remained an internal detail, a quiet advantage. Sharing it openly might invite criticism from traditional engineers who still distrusted welding on aircraft aluminum. So the pre-fit alignment method stayed in-house, known only by those who used it. Behind the statistics and noise, Mildred Sisk continued to work her shifts like everyone else. She didn't lead teams or give speeches, she simply did her job. But the supervisors who once scolded her now treated her with quiet respect. She had become a symbol of what the war industry had learned, that innovation didn't always come from blueprints. Sometimes it came from the factory floor, from people who refused to accept that something couldn't be done faster or better. Her story never appeared in the newspapers, yet among her co-workers, it carried more weight than any headline. The end of 1944 brought both triumph and exhaustion. Willow Run had achieved what few thought possible, turning out one bomber every 5 hours. The production lines ran with almost mechanical precision. The plant's cafeteria served thousands of meals a day. Its lighting consumed enough electricity to power a city. Every corner of the facility hummed with energy. But success came at a cost. Workers endured 12-hour shifts, repetitive injuries, and constant pressure to maintain output. The noise was relentless. Even outside the plant, residents of nearby towns said that they could hear the faint echo of the machinery at night. Yet morale stayed high because everyone understood what was at stake. Every bomber rolling off that line meant fewer Allied casualties, and one step closer to ending the war. Still, the pace raised new questions. Could production be pushed even further? Ford's management wondered if the same method could apply to other aircraft types or even post-war industries. The engineers began experimenting with new torches, automated jigs, and heat controls, taking inspiration from the accidental breakthrough. What had started as an internal improvisation was now shaping the future of mass production. The ridiculous trick had become a principle: small, temporary bonds leading to permanent progress. As 1945 approached, changes outside the factory began to catch up. The war in Europe was turning in the Allies' favor. Cities that once seemed untouchable were now within bomber range. Each raid carried hundreds of B-24s, built at Willow Run, their silver bodies glinting in the sunlight as they crossed the channel. The plant kept sending them out, 5 hours apart, every day, every night. No one paused to think about what would happen after victory. The mission was simple: keep building until it was over. But inside the engineering offices, quiet discussions had already begun.
Some wondered how long the government contracts would last. Others talked about adapting the line for peacetime products, cars, tractors, even prefabricated houses. The war had transformed the nation's factories into engines of innovation, and no one wanted to let that momentum fade. Yet for most of the welders, including Sisk, those questions didn't matter. Their world was the line, the endless motion, the smell of hot aluminum, the pulse of work that had defined their lives since the war began. As February 1945 dawned, the assembly line kept rolling. The rhythm never slowed, the welders never stopped. The lessons of the past 2 years had crystallized into a single truth that everyone understood instinctively. Progress often begins with something small, something overlooked, something dismissed as ridiculous. And for Willow Run, that truth was still sparking, one tack weld at a time. By March, the war's end finally seemed close. The Allied armies were advancing on every front. In Europe, American bombers struck deep into the collapsing German heartland. In the Pacific, the island battles had carried the U.S. Air Forces within striking distance of Japan itself. At Willow Run, the atmosphere was changing. The tension that had driven production for 3 relentless years began to mix with something new: anticipation. Workers who had spent every day under the pressure of quotas and deadlines started to wonder what would happen when there were no more planes to build. The line, however, showed no sign of slowing. Orders still arrived daily from Washington. The Army wanted every bomber it could get before the final push.
Factories like Willow Run were told to maintain maximum operational tempo until further notice. The plant responded as it always had, with efficiency and endurance. By spring, the tack-weld system that had started as an experiment was no longer seen as a trick. It was simply the standard way things were done. New workers were trained in the method without ever knowing its origin. To them, it was just another part of the manual. The numbers from those final months were staggering. Between January and April 1945, Willow Run produced nearly 2,000 bombers, more than most countries had built during the entire war. The pace defied logic. The welders and riveters had become so practiced that the line moved like a heartbeat, steady and automatic. Inspectors walked along catwalks, clipboards in hand, watching finished fuselages glide beneath them on conveyor belts. The sound of engines being tested filled the air. It was an industrial symphony, loud, mechanical, but strangely rhythmic. Mildred Sisk still worked her same shift, though few now recognized how much her idea had reshaped the war effort. To most people around her, she was just another face in the crowd of thousands, a woman in a welding mask moving between the glowing frames of unfinished bombers. She didn't speak about what she'd started. The plant was too busy for reflection. But her fellow welders still used her name quietly when they set up their torches, a small nod to where it had all begun. The scale of the work could be hard to comprehend. Each B-24 contained over 1,200,000 individual parts, each one tracked, measured, and installed by hand. It was said that a single bomber required the work of 1,200 people from start to finish. The tack-weld method had saved hours on every major section, but multiplied across thousands of bombers, it had saved years of labor. The military called it process acceleration. On the shop floor, people just called it getting the job done. By April, rumors began to circulate that the war in Europe would soon end. When word spread that Berlin was surrounded, workers cheered during breaks. Some cried. For many, this was the only world they had known since 1941. The factory, the noise, the shift sirens, the constant urgency. The thought of silence, of the line stopping, was almost unthinkable. Management tried to keep morale steady. Build until victory, posters read. Every plane counts. But deep down, everyone knew the countdown had begun. Then, on May 8th, the news came. Germany had surrendered. The war in Europe was over. For the first time in years, the assembly line paused. At Willow Run, the announcement echoed through loudspeakers. Workers removed their gloves, looked up from their stations, and listened in stunned silence. Then, the entire factory erupted in applause. Horns sounded across the plant. Some people hugged, others cried, some simply stood still. For a few minutes, the massive industrial machine became human again. The next day, production resumed, but it was different. The urgency had faded. Managers told the crews that orders would continue for now, as aircraft were still needed in the Pacific. But everyone could sense that the end was near. The bomber line that had once run 24 hours a day began to slow. Some workers were reassigned, others were told their contracts would soon expire. Government inspectors who had once demanded impossible quotas now spoke in softer tones. The war that had built Willow Run was winding down. By summer, Japan remained the last major target. The air raids on Tokyo and Osaka were devastating, carried out by B-29s rather than B-24s, but every bomber still carried the same industrial DNA, the lessons, tools, and techniques refined at places like Willow Run. Even as the B-24 became less central to the Pacific War, its production continued at full pace until the very end. Planes rolled off the line and went straight into storage depots, ready in case they were needed. The welders didn't question it. They had a job, and they did it. When news of the atomic bombings reached the plant in August 1945, the reaction was mixed. Some celebrated, believing it meant their sons and brothers would finally come home. Others stood quietly, unsure what to feel. Within days, Japan surrendered. The Second World War, the reason for every hour of labor, every spark, every rivet, was over, and with it, the era of frantic production ended too. Almost overnight, the great plant began to empty. Government contracts were canceled. Workers received notices that their services were no longer required. The endless motion of the line slowed, then stopped. The sound that had filled the air for years, the hum of machinery, the clang of metal, the roar of engines, faded into silence. For many, it was the first quiet moment in half a decade. Ford executives faced a new problem: what to do with the largest factory in the world now that its purpose was gone. The company had invested millions into the building, and it could not simply be abandoned. They tried converting it back to automobile production, but the plant had been built for bombers, not cars. The overhead cranes, long assembly tracks, and massive fuselage jigs were too specialized. Reconfiguring it would take time. As the months passed, workers moved on. Some returned to their hometowns. Others found jobs in Detroit's auto plants.
For the thousands of women who had entered the workforce during the war, the future was uncertain. Many were told to give up their positions to returning soldiers. Mildred Sisk was among them. When her final shift ended, she cleaned her welding torch, handed in her badge, and walked out of the plant she had helped transform. No reporter interviewed her. No photograph captured the moment. She simply disappeared back into ordinary life, like so many others whose hands had built the machinery of victory. But her influence didn't vanish. In the post-war years, as industries modernized, the tack-welding method quietly spread beyond aircraft manufacturing. Car factories used it to align body panels. Shipbuilders used it to fit hull plates. It became part of the DNA of mass production, a technique so common that no one thought to ask where it came from. Manuals referred to it as temporary alignment welding. Engineers treated it as standard practice. Yet behind that anonymous phrase was the spark of one welder's curiosity in a wartime factory. In the late 1940s, Willow Run found a new life. The government leased part of the facility to the newly formed Kaiser Frazer Corporation to build automobiles. The same lines that once carried bomber fuselages now carried car frames. The building echoed again with sound, but it was different, softer, slower. The urgency was gone. Still, traces of the old war days remained. Weld marks on the floor, faded posters about production quotas, initials scratched into steel beams by workers who had long since moved on. Historians would later call Willow Run an industrial miracle, the place where America proved it could outproduce any enemy. They wrote about Ford's management, the engineers, the scale of the plant, but rarely about the welders. The story of Mildred Sisk remained buried in old production reports and forgotten memos. Only those who had worked beside her remembered. To them, she wasn't just a welder. She was a reminder that innovation often begins far from the offices of those who take the credit. The tack-weld technique outlived the war, outlived the bombers, even outlived the factory's original purpose. Decades later, when aircraft engineers designed new assembly systems for the jet age, they used the same principle: stabilize before fastening, align before joining. Few realized they were echoing a moment from 1943 when a welder in Michigan had decided to try something different. The ridiculous trick that once broke every rule of aircraft construction had become a foundation of modern manufacturing. And though her name faded from history, her idea never did. It was still there, in every aircraft, every car, every ship, a small, invisible weld holding the world together long after the war had ended. Even as the noise of Willow Run faded into memory, its legacy remained alive in every spark that flew from a torch, every factory that sought to do the impossible a little faster, a little smarter than before.